Hello friends, let us discuss another numerical on the topic that effect of negative feedback on the input and output impedance of different feedback topologies. This is another example. See, figure, that is this figure, shows the circuit of a negative voltage feedback amplifier. If without feedback AV, that is basic amplifier gain, that is for this op amp, gain for this op amp is 10,000, then and Z in, that is input impedance of the basic amplifier block, is 10 kilo ohm. Z out, that is output impedance of the basic amplifier block, is 100 ohm. Find feedback fraction, gain with feedback, input impedance with feedback, and output impedance with feedback. So the first step is you have to identify the feedback topology. Here it is written that negative feedback voltage amplifier. Okay, so sometimes it may not be written in such a way. So how to identify what type of feedback topology is this one? So you know the rule. See, we are taking the output voltage E output across RL. So this will be plus, this will be minus, and see the feedback network is basically this one. You know from the concept of practical feedback network, I have already discussed this circuit. So this is basically feedback network. Okay, so you can say this generates the beta or feedback factor. So see, the starting point of the feedback network in the output side and the output voltage are at same node. So this is basically voltage sampling. And see, this signal, this AC signal, suppose Vs, is coming from the function generator, and this is the input for this basic amplifier block Vi. Now see, here across 10 kilo ohm we are taking the feedback voltage Vf. Now to write the equation of the error signal or the equation of Vi, what we can say? We have to apply KVL in the input loop. So we can say Vi equal to Vs minus Vf. Basically, if you apply KVL, you will get minus Vs, okay, plus Vi plus Vf equal to 0, equal to 0. So from here we can say that is Vi equal to Vs minus Vf. So to get the expression of the original input of the basic amplifier block, we have to apply what? KVL in the input loop. So no doubt this is series mixing. So this is voltage sampling series mixing feedback topology or voltage series feedback topology. Clear? So this is voltage series. Now see, we will draw the basic amplifier topology, basic feedback topology from this name. So voltage series. Okay. So for voltage, what is signifies? It indicates that in the sampling network we sample voltage, and you know that how we sample voltage in parallel. Okay, because in parallel voltage remains unaffected, and series means the mixing network is basically series network. Okay, so we have to draw a block diagram of or a feedback topology for which the output is shunt type and input is series type. Okay, so basically we can get this. See, the input mixing network is series type and output sampling network is basically shunt type. So we have to deal with this feedback topology. We have to calculate the input impedance with feedback, output impedance with feedback, overall gain for this type of feedback topology. Clear? Now let us discuss. See, this is the this already we got in our previous video, that this amplifier, this practical feedback network is basically voltage series feedback topology. Now, as you know from our discussion of practical feedback topology, this is feedback voltage, okay, and this is output voltage. So we can apply what? We can apply voltage divider rule, that is voltage across R1, and we can get the beta or feedback factor, that is beta equal to what? Beta equal to Vf, that is feedback voltage by output voltage, that is equal to what? R1 by R1 plus R2. Just simple application of voltage divider rule. Clear? Now what is R1? R1 equal to 10 kilo ohm by 10 R1 is 10 kilo ohm plus what is R2? R2 is 90 kilo ohm. So units will be cancelled and you will get beta by solving calculator as 0.1. Clear? So we got the feedback network as 0.1. Then our first of all, this is the feedback fraction we got, that is 0.1. Then gain with feedback. So what you know for the formula for gain with feedback? That is A by 1 plus A beta. This is for negative feedback, and the practical feedback network which is mentioned in this one is basically negative feedback, because see here, what is that? This is Vs minus Vf. So basically we can say Xe, that is error signal, which is this one, is basically Xs, that is original source current or voltage which is coming from function generator, minus Xf. So this is the expression of error signal for negative feedback. So this is basically negative feedback. So for negative feedback we know that the overall gain is A by 1 plus A beta. Now see, simple substitution. What is A value? A value is given as 10,000. So substitute that and you will get 10,000 by 1 plus 10,000 into beta. What is beta? Beta is 0.1. Just to calculate it. So 10,000 into 0.1. So solve this by calculator and you will get the overall gain as 10. Okay, this is the overall gain of this voltage series practical feedback network, or this voltage series feedback topology. Clear? Now see, now we have to calculate the input impedance with feedback and output impedance with feedback. Okay, I told you the method. See the input side, the mixing network is in series, and in series the impedance increases, and any increase in any parameter in the feedback amplifier is basically simply multiplication of 1 plus A beta. So the new impedance will be Zi, that is the input impedance of the basic amplifier block without feedback, into 1 plus A times beta. Okay, this thing you know from my theory. Okay, theory videos. So what is Zi? The input impedance is given, see, 10 kilo ohm. Clear? So it will be 10 kilo ohm into what is 1 plus A beta. A is given as 10,000. Just simple substitution of values from the numerical. 10,000 into what is beta? Beta is basically 0.1. Clear? Now solve this by calculator. You will get Zi as so this is the input impedance. After solving by this expression by calculator, you will get this value. Okay. Now we got the input impedance. Clear? Now we have to calculate the output impedance. See, the sampling network is in parallel, and in parallel I told you that the impedance decreases. How much factor? By 1 plus A beta. Okay, because any decrease in any parameter in feedback amplifier module, just you have to divide that parameter of the open loop gain, open loop amplifier by 1 plus A beta. Okay, so the new Zi output with feedback, this is called ZOF, that is Z output with feedback is this one, and this is called ZIF, that is input impedance with feedback, that is Zi into 1 plus A beta, because here in series impedance increases, and for Z output with feedback, that is output impedance with feedback, is basically output impedance without feedback by 1 plus A beta. Now see what is Z output for the basic amplifier, that is 100 ohm. Just simply substitute the values, so it will be 100 ohm by 1 plus what is A? A is 10,000 into what is beta? Beta we calculated as 0.1. Solve this by calculator, you will get 0.1 ohm. Clear? So the output impedance with application of the feedback becomes 0.1 ohm. So we got all the values, that is beta for the feedback network is 0.1, AF or overall gain with feedback is 10, and the input impedance with application of feedback is this one, and output impedance with feedback is this one. Okay, so this is how you have to solve any practical feedback network. I have uploaded some videos on the practical feedback network topic. You can check from there. You can able to learn how to calculate the beta or feedback fraction or feedback factor. Okay, and just then you have to identify the feedback topology. Then the same rule, if there is series connection of any network, then obviously the impedance will increase by a factor 1 plus a beta. If there is shunt connection anywhere, then the impedance will decrease by a factor 1 plus a beta. Clear? This is how you have to solve this type of numericals. This is all for this video. If you have any doubts, you can ask in comment section. And if this video help you for your preparation, please like, share and comment, and subscribe my channel for more upcoming videos. And don't forget to press the bell icon. Thank you for watching.